Okay, hello everyone. Welcome to this lecture of computer system security. We are going to continue our discussions about authentication. I'm just going to give you a very quick review about the authentication and kind of steps that we need in authentication and what we have covered over the past week, and then we continue. If you remember, we defined the authentication as a service of establishing trust between two entities. Of course, one might be the client that requests for a service, and the other one is a server that offers some service. And we said that there are two major uh, steps in performing authentication. One is the registration, at which the user or the client registers itself and shares that information with the server, and server takes a log of that information for future kind of accesses for future authentication. And then the second phase is the actual authentication, that for the second or third or fourth or later on times, the user comes and provides that information, and the server checks, and if server uh, verifies that information, server kind of gains or grants access to the client, and client can now use that service. So we've talked about this, and we've talked about the general model of authentication that we have. We also mentioned to the fact that for having a successful authentication, we need something unique, some piece of information unique at the client or customer side, which might be something that the individual knows, something like a password. And then we talked about password-based authentications or PIN or answer to some questions. So we've already covered this part. And today in this week's lecture, we're going to talk about the cases that authentication is based on something that the individual possesses, that we call them a token. So we will be talking about token-based authentication today and in the next video, and you'll see how tokens can be used for authentication and what are the different classes, what are the different types of tokens, and what might be the some of the kind of potential issues or problems with token-based authentication. Okay. Okay, we've talked about this stuff. Let me jump to the. Okay. In general, we have when we say a token or token-based authentication, we said that we are talking about something that the uh, user or the client possesses, something that you have in your hand, and it is something physical at this type of authentication. We are not talking about, for example, a piece of information. Of course, a piece of information is there as well, but we are talking about something physical, something that you can touch it. And for example, this is an RFID tag that might be used as a authentication token, or here is, for example, a card that might be used for authentication, and also we have smart cards that we will be talking about them. But the common feature about all of them is the fact that there are physical objects, physical things that uh, you can hold in your hand, you can physically touch them, and you can have with them some in different places to get that authentication done. But in general, we have two types of tokens. One of them, which is the kind of easiest in terms of talking about, is the passive tokens, that they just serve as a portable memory. Passive tokens, for example, the major or the easiest example of them are these RFID tokens that here you see I put some of them in this figure, and they work based on making them close to some reader. For example, in some departments, you may have entered this. In some departments, you want to enter the building, or you want to use the, for example, let's say the elevator. it's not open for public. You just need to have a tag with you. If you close the tag, the elevator keypad accepts your key, otherwise it doesn't work. So this is a physical token that we may kind of hold in our hand in order for doing some type of authentication. Or for example, some of the hotels use some types of cards to get access to the room. And that card might be something like this. You put it somewhere, or you swipe it somewhere, or you just make it close to that reader. Again, that's, of course, the technology might be slightly different. The cards that you put them in a reader like this, they work based on some barcode, and the barcode, there are some barcode reader here in this kind of reader. Or for those hotel rooms that you just take the key close to the lock, they're working based on RFID. Of course, they're easier to work with. Or you may have them kind of entered into a specific reader like this figure. But what is common for all of these is that when we talk about passive tokens, we are talking about basically memory cards. A passive token is basically a memory, a static memory that just stores a unique ID which is being used for authentication. The passive token, whatever it is, if it's a RFID token, or it's a card shape, or it's a card even with some chip, the unique property is that they just store the data, and they are not capable of processing anything. So the data or the communication between the token and the reader, they're just a static one, and the token here just works as a memory, as a static memory or memory card for us. They might have even some internal circuitry. The memory might be some internal thing based on some internal circuitry. But even though they have some circuitry, their circuitry is not capable of processing something. And like I said, it just stores the data and represent the data to the reader, and reader might be whatever. Of course, they're good, and they're kind of easy to work with, because you just need to make them close to the reader in some cases, or put them in a specific place like this, and then you're good to go. You get access to that service, or basically you're authenticated in that case. But in terms of security, they are not very highly secure, because whoever possesses the token, they may get access to that service. And drawbacks of passive tokens are here. They require a specific or special readers. Loss of token is a major kind of drawback, is a major challenge, and user dissatisfaction, because of sometimes the readers might not be easy to work with. So these are the passive tokens that, like I said, we also know them, or we also refer to them as memory cards. Okay. In contrast to memory card or passive tokens, we have smart tokens. We don't call them active tokens, because active here doesn't make sense. They interact with the reader, so that's why we call them passive tokens. Yeah, and like I said, the major difference between the smart token versus the passive tokens is that passive tokens, they do not perform or conduct any interaction with the reader. However, in a smart token, we have a series of interactions between the token and the reader. Okay, how that happens, how the smart token perform the interaction? Of course, there should be some type of digital system or processor there. In terms of kind of processing capabilities, they sometimes, or let's say most of them, they have some embedded microprocessors on them, or embedded microcontrollers on them. They might be, for example, ATM cards or debit cards. They are all kind of examples of smart tokens that we possess, and we use them for authentication. Here you see some other examples of smart tokens that we'll be talking about, different types of them. And sometimes they also have some keypads, like here that you see in this smart token. You enter something, and it's even better because if you wanna use this device for authentication, and this device is supposed to generate some password for you, and that password is going to be transferred to the server. But if you want to use this, you need to enter some password on the device itself. So they might be even used as a calculator or something, and they have a keypad. Another kind of important feature about the smart tokens is that they should have some type of user interface, because they are smart. They're going to they're supposed to perform or conduct some type of interaction between the client and the authentication server. So for that kind of multi-step or multi-level interaction, there should be at some point the user involved. So for that, we say that there are some interfaces between the device and the user. Here are, for example, on these examples, here is the interface. You have a small LCD, and that LCD shows something. We'll talk about different kind of types of smart tokens, and you see that this might be the password. Or here you have some keys that you can press them. Here you have only one key, which will reset the system and generates a new password for you, and so on. And also, they should have some type of electronic interface. The electronic interface will be used in order for the token to communicate, to talk, to negotiate with the authentication server. So this device is supposed to be used by the user in order to get access to some services. And it is supposed to let me or enable me be authenticated. So whatever password or something it generates, in most cases, I, as a user, I'm not, I don't need to kind of enter that password or give that password manually to the server. The device directly communicates with the authentication server. So let's say this is authentication server, and I'm the user, and the user enters something here, and the password is being automatically transferred to the or the piece of information that might be a password or any piece of information, which is any unique information which is going to be used for authentication. That thing will be sent to the authentication server, and an authentication server authenticates this device, and through the device, the user which is associated with the device. So they have some type of, these are the major properties of smart tokens. They have some types of embedded processors or embedded computers on them. They have some type of user interface, and they should have some type of electronic interface. Okay. Now let's talk about how the authentication may happen in smart tokens. When we talk about a smart token, authentication may happen through a static approach. In a static approach, the user, this is what happens. The user authenticates himself to the token. So this is the first step. I'm the, for example, like what you see here. I'm the user of this device, and for example, this is a token from HSBC Bank, and I want to use it. When I turn it on, I enter some password. For example, this is my password. I enter my password, and this way I authenticate myself to the token, and the token authenticates me to the authentication server. That's it. That's it. And the user, the device tells the authentication server that this is a authentic person, and now I have access to the whatever services I'm seeking for. Uh, when I authenticate myself to the uh, device, to the token, the second part, so this is the first part, let's say step one, user authenticates himself, this is the user, for example, to the device. In step two, device authenticates himself to the server. Step two can be done similar to, for example, passive tokens. So there might be some code here on the device, like some hard-coded password, like whatever you have in, for example, RFID, but that code is not going to be transferred unless the user authenticates himself, unless the user enters the password. So this is called the static authentication protocol uh, between a smart token and an authentication server, uh, which is easy and kind of convenient, but of course it might have some kind of security issues. That's why we also have dynamic. The second authentication method is dynamic password generator. Dynamic password generators, they are again tokens, physical devices that we may kind of hold, we may have in our hand. And the way it works is this: the token generates unique password periodically. For example, every minute, every second, or every unit of time. And the generated password is entered into the computer system, into the authentication server. It might be entered manually using the kind of the user's hand. I authenticate myself to this device. It shows me a password here, and then I take that password, I enter it to the authentication server, and that way the server allows me to go through to kind of pass. Or the password might be submitted from the authentication token, from the smart token, to the server directly. So this guy has some Wi-Fi or some type of network and just sends the password directly to the authentication server. And I don't have to take the password and type it or something, which is first of all might not be easy because sometimes the lengths of these passwords are kind of long, and secondly might be unsecure. So this is dynamic password generator. And the reason we call them dynamic, the major difference between this item 2 and item 1 is that here, what the data which is being used for authentication, whatever it is, that data is static. Let's say I have a code of, let's say 1234, for example, and this is the code that my token sends to the server, okay? Or it has a this ID that the reader of the authentication server reads that. If I use this approach, static approach for authentication in some smart token, uh, in the first authentication, authentication number 1, authentication number 2, or authentication number 10, in all of them, the same ID or the same password is being uh, transmitted from the token to the authentication server. So the authentication server always receives the same thing. So that's why we say this is static. I may have the option to change my password. I'm using this token, this is a smart token that works under static. I would have the option to change my password to authenticate myself as a user to the token. But the data which is being sent from the token to the server would be always the same. That's why we call it static. However, in dynamic password generator, the password which is being shown to me as a user, and I'm supposed to manually enter it, or which is being sent from the token to the authentication server, that password is different at each authentication trial. So the first password might be 123. The second time that I'm gonna access to that system, my password is something else, for example, 9824. So the passwords are changing dynamically. And the way you may ask, so how the authentication server will know the next password? Because of course the password, this guy generates a password. Let's say the first password is this one, the second password is this one, and so on. So how the authentication system is supposed to know the second password, third password, and next password in general? The answer is there is a unique algorithm on the token and the authentication server that generate passwords. So the first password it generates is 1234. So 1234 is being generated here, and the same password is being generated here. So the authentication server is waiting for 1234. Next time, the next password this guy generates is going to be, for example, 9824. The same, since the same algorithm is used here, the authentication server is also waiting for 9824. And this is the way that smart tokens can dynamically generate new passwords. Of course, like I said, the algorithm should be similar. If you're using algorithm X, the same algorithm X for password generation should be used here. That's the first thing. The algorithm should be exactly the same. And secondly, the algorithm needs some type of synchronization. They should start from the exact same point, and they should generate an exact sequence of passwords, which, like I said, it is called as a synchronization manner. So there should be some mechanisms of synchronization between the smart token that works under the category of dynamic password generator and the authentication server. We will be talking about it. This synchronization is a kind of is a challenge. I'm not going to say is a big challenge or unsolved challenge, but it is a challenge. Another mechanism that the smart tokens may use for authentication as authentication protocol is challenge response authentication. In a challenge response authentication, there is no sequence of known passwords between the token and the authentication server, and they work this way. The user, here this figure kind of shows different steps. Let's go through the figure. In the first step, the user requests access to some services to the authentication server, and authentication server issues some challenge, issues some which is basically some data. It returns some data, and that data is just a number, for example. And in step 3, if it might be, for example, through a smartphone, the challenge is being transferred to the token. The challenge is being transferred to the token, and the token calculates something based on that challenge. For example, let's say you want to get access, and the server sends you, for example, 234. That's it. The token here knows that, for example, should calculate hash of 234, sorry, or calculates, for example, something to the power of 234, and then returns that thing to the authentication server. That thing it will be used as a password. So the algorithm that token is going to apply on that challenge is known by the token and by the server. So the server sends some challenge data or challenge number, and the token knows what to do, what computations are supposed to be done on that challenge data. The token performs that kind of computation, applies that algorithm, finds the results or output of that algorithm, and returns the output of that algorithm to the authentication server as the response. So that's why we call it challenge response. And once the response is received by the server checks that. For example, server also is waiting for, let's say, 3 to the power of 234 or hash of 234. If they match, it means that, okay, this token is a valid token and it's being registered before, so the user will get the access and will pass through the requested services. So this is called authentication through challenge response in smart tokens. Okay, let's get back to the problem I mentioned. I said that in password generation based authentication in smart tokens, one issue is synchronization. And I've opened the problem. I said that here we have the, for example, let's say this is the, for example, this is a smart card and this is a server, and you want to get authenticated. There is a sequence of password, for example, 1234, 2829, and so on, which are known at both sides. And it's not like this that we have generated these passwords before. No, the token and the authentication server, they just start from the same point. They are synchronized using the same algorithm. So they generate the same sequence of passwords. And every time the token uses one password and sends it to the authentication server, and an authentication server is waiting for that specific password, because the authentication server also generated that password, and matches them against each other, compares them against each other. If they match, it means that the token is legit and the user gets access. Like I said, this is the scenario, and based on this scenario, it is very obvious that the synchronization here plays an important role. If the token and the authentication server gets out of the synchronization, uh, for example, the token starts generating this password, and the next password is something, for example, 7281, here 7281, and the server starts from here. So the first password will be matched, will be checked against this one, and the authentication fails. So they should be synchronized. The synchronization is a very important issue here. Otherwise, the authentication will not go through. So how to get the authentication server and the token synchronized? There are multiple ways for doing that. The easiest thing to do is time-based synchronization. In a time-based synchronization, the token and authentication server are being synchronized using some kind of initial time. There is a timer on the authentication, on the token, and that timer is being synchronized with the same timer on the server. And that timer is being used as a seed number, as a seed value in generating the password. So since they use the exact same seed, they generate the same passwords. And the timer, of course, it counts by the time. And since it counts, the next password which is being generated again will be the same for both parties, both sides. Like I said, it's a timer. It might be a clock, internal clock, which must be remain synchronized, and that will be used in the password generation process. This, of course, works, and some of the smart tokens use this approach. But the problem here with this is if you have a token like this, your token should have some type of battery, because it needs to keep the time, and the time should be synchronized. For example, here in these tokens that you see, if you have ever used some of them, you'll see that back of them there are some type of small batteries, and those batteries are used to keep the time, so that the password they generate will be uh, the same as the password that the authentication server generates. Uh, and if due to any reason the password dies, or for example you disconnect the password for a moment, whatever, the time will be reset and the token now will be out of the synchronization with respect to the authentication server, and the future or the next passwords which are generated by the token will not match with those of the authentication server, and the authentication process fails. So it's very important, if you are using a token like this, it's very important to keep their battery protected. If you're using one of them and you, for example, accidentally just remove the battery for let's say even a second, it doesn't matter how long it is. The timer resets, the internal timer resets, and after internal timer resets, now your token is out of synchronization with the server and you cannot use it anymore. And mostly for fixing that, you need to go to some agent somewhere, to, for example, your bank branch, and they put it on another device and they get it synchronized, which basically they do it in the at the first place at the time of issuing the token. When you ask for the token, they get it synchronized with the server. So that's a time-based synchronization. Another way of synchronization is event-based synchronization. In that case, there is no internal timer. They use some, let's say, counter, and of course they start from 0, and then this way they avoid the kind of requirement for time synchronization, which is very difficult to keep it. And the user presses a button to generate a one-time password, and the timer of course increases. If you use that password, after being authenticated by the authentication server, the server also increases that counter by 1. For example, let's say they start from the counter 100. Let me clear some of these. Yeah. Uh, let's say, for example, the token and the authentication server, they start from a counter 100, and then you press a button, you get the password, you use that password, and the authentication server lets you go in, and now both of the counter goes to 101. And the next time, the next password which is being generated is based on 101. Of course, the next password, both of them generated based on 101, it's gonna be kind of a valid password. You apply it, you get authenticated, and you both of the counters goes 100 or 102, and so on. And this way, there is no need for keeping that internal timer synchronized. This works, but there is a common problem for that. There is a kind of let's say major problem for that, and that's the time that I generate a password. Let's say 102. I generate the password. I push the button. The token generate a password for me, and the counter of the password becomes 103. But due to some reason, I don't use that password, and I don't kind of send it to the server. And of course, that password might be lost at some point, or I may lose it. If I come and push the button, press the button another time, now another password is going to be given to me based on the number 104, and the server is waiting for a password based on 103. So the problem here in this event-based synchronization is, if you generate a password, you should of course use it. That password should be used. If you lose that password due to any reason, you'll get out of synchronization with respect to the authentication server, and that can make a problem. And the third way for synchronizing smart token that they work based on synchronization or dynamic password generation is continuous authentication. In a continuous authentication, it is basically, it has a limited application, and it is being used by systems that continuously validate the user identity. And they mostly work based on the proximity of the token with respect to the authentication server. So if you are close to that authentication server, when I say you, I mean the token, of course. You as a user, you possess that token is with you. For example, it is in your pocket and you are using that token. If you're in a close proximity to the authentication server, you are being authenticated continuously. You are being identified all the time, and the server trusts you. The moment uh, you get far from the authentication server and the token kind of gets disconnected or is not readable or is not accessible by the authentication server, uh, they go out of synchronization, and you need to redo everything. So this can be also, of course, classified as other type of authentication. This might be, for example, this can be happen through some passive tokens as well, tokens based on, for example, RFID. You don't need, if you want to, or let me put it this way, if you want to synchronize the token and the authentication server this way, you basically don't need to go with the smart tokens. You can go with the normal token or passive tokens, like, for example, RFID. That might be enough. You don't need to pay for smart tokens. You just go and get a RFID tag, which is very cheap. Sometimes they're below $1, and that might be used for proximity-based authentication. So we are done with the types of kind of tokens. We talked about passive tokens and smart tokens, and we've talked that smart tokens may take 3 different approaches for authentication: static password, password generation, and challenge response authentication. And now what I'm going to do is to give you some examples of smart tokens, some real examples of smart tokens. The first smart token we are going to talk about is a USB token. You have a USB device that, of course, you can plug it into your system, and that USB, it contains some information. And that information will be used for authentication. Like I said, it's a device that you plug it into your computer, and it uses a public key infrastructure, or PKI technology, and it contains a certificate, which is kind of signed by a trusted uh, certification authority. Of course, they are different than other kind of smart tokens. They don't generate password for you. That certification is kind of the reason that server trusts you and give access to you. And of course, that certification is generated based on some keys which are not available to other people. So you cannot regenerate them. Yeah, the device is encoded with your digital signature. So your digital signature is also involved. So you don't have to type anything. So you just plug the device, the certificate is there, and your digital signature is there. And based on the certificate, the kind of authentication server kind of grants access to you. And since your digital signature is there, you cannot kind of deny later that it was me. And since your digital signature is there and the certificate is there, no one else can use it. Yeah. So this is one example of smart tokens that it used to be used. We have them in some applications even now, but it used to be used more than today's. And for example, some applications. For example, you write an application and you want to protect it. You provide the user with a smart token like this. And for example, you have written an application which is very important to you and you are worried about copyright issues. You provide the legit user with the token like this, and the application only works while the token is plugged to the system. Okay, this is one example of smart tokens. And of course, here, the signature is kind of involved and the certificate is involved. And the certificate um, can be kind of invoked later, can be canceled later. So we can have the token physically, but the token is not legit anymore if the authentication server decides to do that. Okay, another example that I intentionally put it as a second example because this is going to take a little bit longer time, are smart cards. Smart cards are basically the most important category of smart tokens. In terms of appearance, you can think about credit cards. They are mostly in appearance or in size of credit cards, and they almost have all of the features that I mentioned. They have electronic interface that accept, stores, and send information through a reader. And the way they work is the user insert the smart card into a reader to begin a communication. And they may use any, or let's say in some cases, even they may use multiple authentication protocols. And of course, the information contained within the smart card provides authentication information. And in most of cases, like I said, in terms of hardware, they contain a full computer in them. And when we say a full computer, it means a processor. They have a processor, they have memory, they have input output ports for being read and for being written. And that way they kind of provides information for authentication. And here are the types of memories that we can find in smart cards as a smart tokens. They have some ROM or read-only memories that it may store some data that shouldn't be changed for the whole life cycle of the card. They have some E2P ROMs. They have some information which are normally supposed to be kept safe, but that's a few cases you may want to change them. For example, you have your debit card, or let's say yeah, even in some credit cards, you may have set a PIN, and of course the PIN is a number that you don't want to regularly or frequently change it, but at some point you may want to change or update your PIN. That PIN is being written on an E2P ROM, or electrically erasable programmable read-only memory. So you don't change it frequently, but at some point you may want. And also they have some random access, or RAM, which is a main memory, and it's being used by the processor for for following the protocol between the smart card and the authentication server, or the reader device. So they have kind of different classes of memories on them that helps that full computer that I mentioned here to work. Okay, Let's talk about the kind of steps that happen after you insert your smart card into a reader. After you insert or you swipe your smart card, uh, mostly this is the case for the time that we insert the smart card. After we insert it, a reset signal or a reset message is going to be sent from the reader to the smart card, and that reset message is going to initialize some parameters, like for example the clock value or some other initial values. I should mention here that the figure, this figure in the book has a kind of typo in it. They just misplace smart card and card reader. They're misplaced in the book. So if you're if you're looking at the book, please pay attention to that. That the smart card reader should be here, and the uh, smart card itself should be here. In the book, they're kind of swapped, and that's not right. Uh, so after you insert your card here from the smart card reader, a kind of reset signal is being sent, or a reset message is being sent to the smart card, and the smart card responds with a message which is called answer to reset. So this is answer to reset message, and the answer to reset message, it has some information in it. First of all, it acknowledges that yeah, the smart card got reset and got initialized, and the parameters sent by the reader are just captured by the smart card, and they're being used by the smart card in the future of these. Let me erase the stuff. So yeah, the first thing it mentions is that yeah, um, it acknowledges and it kind of uh, get the smart card ready for that authentication process, and also it defines the ATR message, answer to the reset message. It defines parameters and protocols that the smart card support. So this smart card may support, for example, let's say dynamic password generation, or it may work only under static password generation. So how the smart card tells the reader that what type of authentication I support, all of that information go to ATR message, and after the ATR message is received by the card reader, now the card reader better knows the smart card. There might be some flexibility from the smart card. If that's the case, the card reader now may change the protocol uh, and may ask for some changes. That happens through something which is called protocol type selection message. So the card reader sends this. So if I, for example, mark this as A, this is A, protocol negotiation or protocol type selection. Packet goes from the card reader to the card, and then card replies that of course there should be some answer to that message. Card either accept or say no or whatever. They come up with some specific protocol and details for authentication, and then the actual authentication starts happening, which is the which might be the way it should be. For example, the smart card generates passwords, send it to the card reader, and card reader responds, or vice versa. It depends on the application. The smart card might be the initiator or might be the starter, or the card itself, or the reader might be the starter or initiator, or the smart card itself might be the initiator. It depends on the type of protocol kind of they agreed upon, and that's why you see this arrow here. It tells that they might be swapped or they might be exchanged. The command might be sent from the card reader to a smart card, or the smart card may say may send something and may wait for the answer from the card reader. And after the authentication is being completed, and now the user gets access to that service, whatever it is. Okay, the next thing that I guess we probably can put it for, yeah, it takes more than maybe 10-15 minutes. So let us stop here, and I'm going to talk about electronic identity cards, or EIDs, as another example of smart cards. These are basically something like a smart card, but they're mainly used by government and by kind of national agencies in order to authenticate the citizens. They are called electronic identity cards, and we'll be talking about them in the next video. So thank you for attending this video and watching this video, attending today's class, and please use uh, APDU as the code for, as the attendance code for today's class. APDU, all uppercase. Thank you and have a great rest of the day.